In 2013, a star 1,470 light-years from Earth lost 22% of its light. Not for a fraction of a second, for days. Then it came back. No known planet can block that much light. No known eclipse can do that. And the dip did not repeat. The star is called KIC 8462852. The Kepler Space Telescope had been watching it since 2009, alongside about 150,000 other stars in the constellation Cygnus. Its job was simple: catch the tiny dips in light that happen when a planet crosses in front of a star. Most dips are small. A Jupiter-sized planet passing in front of a Sun-like star blocks about 1% of its light. An Earth-sized planet, less than 1/100th of 1%. Kepler was built to see those signals, and almost nothing else. KIC 8462852 itself looked ordinary in its catalog entry. An F-type main sequence star, about 1.5 times the mass of the Sun. Hotter than ours, slightly brighter. Nothing flagged. Until the light curve. Around March 2011, the star dimmed by about 15%. 2 years later, in early 2013, a second event went deeper. 22% of the star gone. For a few days, then back. For context, a transiting planet does not do that. Even a brown dwarf, a failed star several times the size of Jupiter, would block only a few percent. To dim a star by 22%, you need something almost half its diameter, sitting directly between the star and Earth. There is no known planet that big. The shape of the dip was wrong too. Real planet transits are clean. A smooth dip down, a flat bottom, a smooth dip back up. Like a U with rounded corners. KIC 8462852's dips were asymmetric, jagged. Some had multiple bottoms, as if several objects of different sizes were crossing the star one after another. And the timing was irregular. No period, no repeat, just events. Kepler watched this star for 4 years. It saw a handful of these events. No two looked alike.
The data was odd enough that it did not move through automated pipelines. It was the Planet Hunters Citizen Science Project, volunteers visually inspecting Kepler light curves, who flagged it first, years before any paper was written about it. The lead astronomer who took it from anomaly to publication was Tabitha Boyajian, then at Yale University. The official name of the star is KIC 8462852. The unofficial names are Tabby's star or Boyajian Star. Most astronomers use one of those two. When Boyajian's team submitted their paper, they walked through every conventional explanation they could think of. Instrument error, a passing planet, a close stellar companion, a cloud of debris from a recent collision. Each one was tested. Each one was eliminated by the data. The paper enumerated the remaining possibilities. The most plausible scientific one was a swarm of fragmented comets passing in front of the star. The least plausible, but not removed from the table, was something built. That is the line that changed everything. A few weeks before Boyajian's paper was made public, Jason Wright, an astronomer at Penn State, was working on a completely separate study. His team was trying to figure out what an advanced alien civilization might look like through a telescope. The reasoning is old. It goes back to the physicist Freeman Dyson in 1960. Dyson argued that any civilization that keeps growing eventually needs more energy than its planet can provide. The logical next step is to capture energy directly from the star, not by living on its surface, that is impossible, but by surrounding it, building solar collectors, a lot of solar collectors, enough to wrap a large fraction of the star. This idea got the name Dyson sphere, even though Dyson himself preferred to describe it as a swarm, a cloud of independent structures, each one orbiting the star, each one absorbing a piece of its light.
From far away, a Dyson swarm would not look like a sphere. It would look like a star that occasionally goes dark in strange, irregular ways, as different pieces of the swarm pass in front of the disk, with no fixed period, with dips of unusual depth, with shapes that have nothing to do with planetary transits. Wright's team had just published a method for searching for exactly this signature in Kepler data. Then, Boyajian's light curve appeared. Wright did not claim that KIC 8462852 was a megastructure. What he wrote, in a follow-up paper that made global headlines in October 2015, was that the star's behavior was consistent with the kind of signal you would expect from a swarm of constructed objects, and that the hypothesis should not be excluded without further data. Almost no astronomer ever writes that. The press cycle was immediate. The phrase alien megastructure was attached to KIC 8462852 within hours. Tabitha Boyajian gave a TED Talk that has since been watched millions of times. A crowd-funded campaign was launched in 2016 to keep large ground-based telescopes pointed at the star around the clock, so the next dip could be observed in real time in multiple wavelengths while it was happening. That is the experiment that broke the megastructure hypothesis, or at least broke its strongest version. In May 2017, a new dip began. The observers had time. They had filters. They watched the star fade in red light, in blue light, in ultraviolet, in infrared, simultaneously. The result was clear. The star did not dim equally across all wavelengths. Blue light was blocked more than red light. The dip was wavelength dependent. That single observation rules out a solid object. A Dyson swarm made of opaque panels, or a planet, or a brown dwarf would block every color of light equally. Anything large and solid would behave like a hard edge. What does dim more in blue than in red is small particles, dust. The leading scientific explanation today is that KIC 8462852 is surrounded by an uneven cloud of fine material, possibly the debris of a planet or a swarm of planetesimals that was disrupted, possibly an unusual circumstellar shell. The cloud is irregular, clumpy, and not uniformly distributed in the star's orbital plane. As different clumps drift between us and the disk, they bite irregular pieces out of the light, with the exact wavelength signature of dust. This explanation accounts for almost everything in the short-term Kepler dips. Almost. Because there is a second mystery, and the dust hypothesis does not fully solve it. When astronomers went back into historical photographic plates of the same patch of sky, going back to the 1890s, they found that Tabby's star has not been steady at all. Across more than a century of records, it appears to have faded slowly by a few percent. Across the 4 years that Kepler watched it, it dimmed by an additional small fraction. This is the long-term dimming problem. A dust cloud large enough to cause a century of fading would have to be enormous. It should glow in the infrared as the star heats it from inside. So far, the infrared excess detected around Tabby's star is small. Not zero, but not as large as a thick, dusty disk should produce. Some models propose that the dust is in a very thin, edge-on ring that absorbs visible light but re-radiates infrared in directions we cannot easily see. Others propose that the star itself is intrinsically variable on long timescales we do not understand.
A small minority still leaves room for non-natural explanations, on the grounds that no single dust model has cleanly fit every dataset at once. Since 2017, astronomers have found other stars showing similar irregular deep dips. They are sometimes called Boyajian stars, or in the technical literature, dippers. None of them are as extreme as KIC 8462852, but they are not unique anymore. Whatever process is happening, it is not one star, it is a class. That makes a built explanation harder to defend. The galaxy does not produce identical alien civilizations next to each other. It does produce identical dust geometries.
The current state of the field is honest. The short-term dips are very probably dust. The long-term dimming is partially explained, partially not. The original megastructure hypothesis has been moved out of the leading scientific position, but it has never been formally ruled out by every author. It is sitting in the corner of the room, watched. This is the strange part of modern astronomy. We have built instruments precise enough to detect a 1% dip in starlight from over 1,000 light-years away. We have catalogs of hundreds of thousands of stars under continuous monitoring. We have models for dust, for planets, for stellar pulsations, for binary eclipses, for almost every known way a star can change in brightness. And one star, in the constellation Cygnus, still does not fit cleanly into any of them.
Tabby's star is probably dust. Almost everyone in the field agrees. But probably is doing work in that sentence. The same instruments that ruled out a Dyson swarm are also the ones telling us that something around this star is doing things our models did not predict, and that other stars are quietly doing the same thing. If you spend long enough looking at the sky, this is what you find. Not aliens, not usually anything dramatic, just objects that refuse to behave. And the universe has a way of saving its rarest events for the moments we happen to be watching. Next video. On December 27, 2004, a flash of radiation from across the galaxy reached Earth in less than 1/10 of a second. It was not from a planet. It was not from a comet. And the next one might come from a star we have not even found yet.